A critical point, also called a stationary point, of a function f of x comma y occurs where the surface is flat in both directions. That is, the slope in the x direction and the slope in the y direction are both 0. Mathematically, we set the first-order partial derivatives to 0. Partial f partial x equals 0, partial f partial y equals 0. For the example f of x comma y equals x squared plus 2y squared minus 4x plus 6y. Step 1. Compute the partials. Partial f partial x equals 2x minus 4, partial f partial y equals 4y plus 6. Step 2. Set them to 0. 2x minus 4 equals 0, which gives x equals 2. 4y plus 6 equals 0, which gives y equals negative 3/2. Thus, the only critical point is the point with coordinates 2, negative 1.5. Geometrically, this is the point where the paraboloid turns, similar to the bottom of a bowl. In engineering terms, if F represented potential energy, this point would be an equilibrium position. Further analysis tells us whether it is stable, a minimum, or unstable, a maximum, or a saddle. Once we have a stationary point, we need to know its nature. The second derivative test uses the Hessian matrix, which gathers all second-order partial derivatives. H equals a 2 by 2 matrix with F sub Roman 20 in the top left, F sub xy in the top right, F sub yx in the bottom left, and F sub y in the bottom right. The determinant D equals F Roman 20 times Fy minus Fxy squared decides the type. If D is greater than 0 and F Roman 20 is greater than 0, then we have a local minimum. If D is greater than 0 and F Roman 20 is less than 0, then we have a local maximum. If D is less than 0, then we have a saddle point, neither a maximum nor a minimum. If D equals 0, the test is inconclusive. For f of x and y equals x cubed minus 3xy squared. F sub x equals 3x squared minus 3y squared. F sub y equals negative 6xy. Setting them to 0 gives the stationary points 0, 0, and plus or minus 1, plus or minus 1. F sub Roman 20 equals 6x. F sub y equals negative 6x. F sub xy equals F sub x equals negative 6y. At 0, 0, F Roman 20 equals 0, Fy equals 0, Fxy equals 0, so D equals 0. Inconclusive, a deeper look shows 0, 0 is a saddle. At 1, 1, F Roman 20 equals 6, Fy equals negative 6, Fxy equals negative 6, so D equals 6 times negative 6 minus negative 6 squared equals negative 36 minus 36 equals negative 72 less than 0, so 1, 1 is a saddle. The same holds for the other 3 points. Hence, the function has only saddle points visualized as a twisted Pringle chip surface, where moving along one direction climbs while moving perpendicular descends. When the domain is a closed and bounded set, think of a sealed container. A continuous function must attain both a largest and a smallest value somewhere inside the container. Step 1. Find all interior critical points. Solve partial f partial x equals 0 and partial f partial y equals 0 and classify them. Step 2. Examine the boundary. Replace the boundary equation with a single variable function, often using a parameter, and repeat the critical point search on that curve. Step 3. Compare the function values from steps 1 and 2. The biggest is the absolute maximum. The smallest is the absolute minimum. Example: domain x squared plus y squared less than or equal to 4, a disk of radius 2. Let f of x comma y equal x squared plus y squared. Inside, partial f partial x equals 2x, partial f partial y equals 2y, leads to critical point at 0, 0 with f equals 0. Boundary x squared plus y squared equals 4. On the circle, we can parameterize x equals 2 cosine theta, y equals 2 sine theta, then f equals 4 for every theta. Thus, the absolute minimum is 0 at the center, and the absolute maximum is 4 on the whole circle. The analogy is a rubber sheet stretched over a circular frame. The lowest spot is at the center, the highest is the rim. If the function were more complicated, you would differentiate the one variable expression after substitution to find possible boundary extrema. The method of Lagrange multipliers handles optimization when a constraint ties the variables together like a rope of fixed length or a budget limit. The idea: At an optimum, the gradient of the objective function nabla f is parallel to the gradient of the constraint nabla g. Introduce a multiplier lambda and solve. Nabla f equals lambda nabla g, g of xy equals 0. For f of xy equals x squared plus y squared, with the linear constraint g of xy equals x plus 2y minus 5 equals 0. Nabla f equals 2x, 2y, nabla g equals 1, 2. Set up equations. 2x equals lambda times 1 and 2y equals lambda times 2. From the first, lambda equals 2x. From the second, lambda equals y. Hence y equals 2x. Substitute into the constraint. X plus 2 times 2x equals 5, which gives 5x equals 5, so x equals 1. Then y equals 2. Evaluate f. F of 1, 2 equals 1 squared plus 2 squared equals 5. Because the objective is a distance squared from the origin, the solution is the point on the line x plus 2y equals 5 closest to the origin, exactly what the multiplier method captures. If the constraint were a circle, the solution would be the farthest point, etc. When the region is a rectangle, the boundary consists of 4 straight edges and 4 corner points. The procedure: find interior stationary points as usual. For each edge, hold one variable at its constant extreme, for example x equals 0 or x equals 2, and treat the function as a single variable function of the remaining variable. Differentiate, and locate edge critical points. Evaluate the function at all interior critical points, edge critical points, and the 4 vertices. Compare the values to decide the absolute maximum or minimum. Example: f of xy equals xy on 0 less than or equal to x less than or equal to 2, 0, less than or equal to y less than or equal to 3. Interior f sub x equals y equals 0, and f sub y equals x equals 0, only 0, 0 inside f equals 0. Edge x equals 0, f equals 0 for all y maximum 0. Edge x equals 2, f equals 2y. Derivative with respect to y is 2. No interior extremum endpoints. Y equals 0, f equals 0, and y equals 3, f equals 6. Edge y equals 0, f equals 0. Edge y equals 3, f equals 3, x. Derivative 3. No interior extremum endpoints. X equals 0, 0, and x equals 2, 6. Vertices 0, 0 gives 0, 2, 0 gives 0, 0, 3 gives 0, 2, 3 gives 6. Thus the absolute maximum is 6 at 2, 3, and the absolute minimum is 0 at all points on the axes. In engineering, this could model the maximum power product of voltage and current you can get with given voltage and current limits. A saddle point is a stationary point where the surface rises in one direction and falls in another, much like the shape of a horse saddle or a mountain pass. Mathematically, it occurs when the Hessian determinant d is negative. For f of x, y equals x squared minus y squared. Partial derivatives: f sub x equals 2x, f sub y equals negative 2y. Setting them to 0 gives the only stationary point 0, 0. Second derivatives: f sub x x equals 2, f sub y equals negative 2, f sub xy equals 0. Hence d equals open parenthesis 2 close parenthesis open parenthesis negative 2 close parenthesis minus 0 equals negative 4 less than 0, confirming a saddle. Geometrically, moving along the x-axis, y equals 0, the function looks like a parabola opening upward minimum direction. Moving along the y-axis, x equals 0, it looks like a parabola opening downward maximum direction. In physics, a saddle point can represent an unstable equilibrium. For example, a ball placed on a hill ridge will roll down in one direction but stay level in the perpendicular direction. Visual aids: think of a sheet of fabric pinned at its center and stretched more in one direction than the other. The center feels flat, but the fabric slopes away differently depending on the direction you walk. Exam type problem 1. Find all local extrema of f of x, y equals e to the xy minus x squared minus y squared. Compute partials. F sub x equals y times e to the xy minus 2x. F sub y equals x times e to the xy minus 2y. Set to 0, y e to the xy equals 2x and x e to the xy equals 2y. Multiply the equations. xy e to the 2xy equals 4xy, which implies either xy equals 0 or e to the 2xy equals 4. If xy equals 0, either x equals 0 or y equals 0. Substituting back gives the point 0, 0 as the only solution. If e to the 2xy equals 4, then 2xy equals natural log of 4, so xy equals natural log of 2. Substituting into y e to the xy equals 2x gives y times e to the natural log of 2 equals 2x, which simplifies to 2y equals 2x, so x equals y, hence x equals y, and x squared equals natural log of 2, giving x equals plus or minus square root of natural log of 2, and y equals the same sign as x. Evaluate the second derivative test. F double sub x equals y squared e to the xy minus 2, f double sub y equals x squared e to the xy minus 2, and f sub x sub y equals e to the xy plus xy e to the xy. At the point 0, 0, f double sub x equals negative 2, f double sub y equals negative 2, f sub x sub y equals 1. The determinant d equals negative 2 times negative 2 minus 1 squared, which is 4 minus 1 equals 3 greater than 0, and f double sub x is negative, indicating a local maximum at the origin. At the point square root of natural log of 2, square root of natural log of 2, plugging in the numbers gives d greater than 0 and f double sub x positive, indicating a local minimum. The same holds for the negative pair, giving 2 symmetric minima. Thus the function has one local maximum at the origin and 2 symmetric local minima. Exam type problem 2. Find absolute extrema of f of x, y equals sine x plus cosine y on the rectangle from 0 to pi in x and 0 to pi in y. The function separates. To maximize sine x, we take its maximum value 1 at x equals pi over 2, and to maximize cosine y, we take its maximum value 1 at y equals 0. Since the domain includes y equals 0, the absolute maximum is 1 plus 1 equals 2 at the point pi over 2, 0. For the minimum, sine x attains its minimum value 0 at x equals 0 or pi, and cosine y attains its minimum value negative 1 at y equals pi. Hence the minimum value is 0 plus negative 1 equals negative 1, occurring at the points 0, pi and pi, pi. There are no interior critical points other than where the partial derivatives vanish. F sub x equals cosine x equals 0 gives x equals pi over 2. F sub y equals negative sine y equals 0 gives y equals 0 or pi. These are exactly the points we have considered. Therefore, the absolute maximum is 2 at pi over 2, 0, and the absolute minimum is negative 1 at 0, pi and pi. Degenerate Hessian d equals 0. If the determinant of the Hessian is 0, the second derivative test fails. Don't stop there. Examine higher order terms or use directional analysis. A common mistake is to label the point as inconclusive and then ignore it, possibly missing a true extremum. Missing boundary stationary points. For closed regions, many students only check interior critical points. Remember to treat each edge as a separate one-dimensional optimization problem. In rectangular domains, also check the 4 corner vertices. They often hold the absolute extrema. Symmetry. If the function or the region is symmetric, you can reduce work. Example. For f of x, y equals x squared plus y squared on a circle, you know the maximum occurs on the boundary without any calculus. The minimum is at the center. Lagrange multipliers, forgetting the constraint equation. After solving nabla f equals lambda nabla g, always substitute back into the original constraint. Otherwise, you may obtain spurious solutions. Sign errors in partial derivatives. A small sign slip can flip a maximum into a minimum. Double-check each derivative, especially when the function contains products like e to the xy or trigonometric terms. Using the same letter for different quantities. Keep clear notation for the multiplier lambda versus variables x, y to avoid algebraic confusion. Quick checks, plug the candidate points back into the original function. The numerical values give an immediate sense of which are larger or smaller.